talking to you guys. This is a very vulnerable talk for me, so I just want to say that out loud. You're the first people to ever hear this talk. So I'm getting up here to talk to you because this is one of the projects I'm the most proud of in my career. This was the largest certified EnerPHit retrofit that I am aware of in the world. So we took an 18-story building, 164 suites, and we made this building thermally resilient. We put an exterior envelope replacement on it. We made it essentially independent from the ravages of the winter weather. If we have an accidental failure over Christmas of the HVAC system, no one notices or complains. It is perfectly passive in the winter. And we did a lot of analysis before we did this. We wrapped this building in quite a high R value. We've got medium solar gain windows, solar heat gain coefficient of about 0.32. And we did just a ton of thermal modeling. We used the PHPP tools, and we used thermal comfort modeling. We used a full year of energy data. We used Energy Plus to do some analysis. We used 2040 weather files to make sure that a directive that had come from earlier in the project before I'd gotten on board was going to work. And that directive was, don't provide air conditioning. Passive houses can work without air conditioning. So I was actually a little worried about that. So I did some finagling. I got it converted to heat pumps that wasn't originally in the plan, and I put some air conditioning in it because I was worried. But I didn't put a lot of air conditioning into it. And the thing is, guys, in real life, the building overheats sometimes with the little amount of air conditioning I could put in it. And so we did all of this modeling, like what happened? Did I just do it wrong? So I was doing some reading in preparing for this talk, and I found dozens of studies of other passive house buildings, especially MURBs, across the globe that are overheating at a far greater rate than is predicted by the analysis when we're in the design phase. Here's some citations. This is not for you to read as much as for you to see the density of overheating studies for passive house buildings. And this one I'm going to read to you. So overheating frequency is determined at a dwelling level rather than a room level, but significant overheating is observed in bedrooms, even when dwelling level criteria are met. So that gives you a clue about what's going on. So how did this happen? How do we have standards that lead us to believe that our buildings will work in the summer, and then when we build them, they're not really good at what we were hoping they're going to be good at? So I'm going to actually put this one up first. My number one culprit, my number one suspicion was heat gain, the behavior of the human beings in the space. So EQ Building in 2019 worked with Sidewalk Labs. They have a branch that does energy monitoring in buildings, so they actually know about the energy consumption of 10,000 condo dwellers in downtown Toronto. And they looked at that data, and they looked at what people were doing with their electrical consumption. So you can see here, that's this green curve, that most people are kind of using 3,000, 3,500 kilowatt hours per suite per year, but the 95th percentile uses double that. So if you just make that a 12-hour day, assume that people kind of turn stuff on and off, that's 1.5 kilowatts of internal gains. So 1 in 20 people in these buildings that we're building are going to have the need for cooling of at least half a ton before you look at anything going on in the suite in terms of envelope loads. And if you decide that those people don't deserve air conditioning because they should just turn some stuff off, many of them will decide to be too hot instead of turning the stuff off. And I think that that's okay, right? Who among us has not had a house party where it got very steamy and you had to open the windows and it was still too hot, right? Who among us has not said, my kid needs to have cookies to take to the bake sale tomorrow. I have to bake cookies. I know that it's 28 degrees outside. So we need to be able to live in our buildings. And in a passive building, one of the problems is it's so insulated and the air conditioning system is so undersized that, unlike in a sort of normal building, well, okay, it's going to be hot for an hour or two, my guests will leave, and it'll get cool again. These buildings hold the heat, and it's very hard to cool them down once all of the thermal mass of the space has become heated up. And we'll get into more causes for that later on. So at McNabb, you can see that we modeled, I think Passive House was down here, but this is what my tenants were doing. So the assumption that was in the model was too low, and it was under-predicting the thermal gains, which was under-predicting the amount of cooling that would be required. So the next thing that happens in PHPP in specific is that we model the entire suite, or sometimes even the entire building, when we're looking for that maximum 15 watts per meter squared certification criteria. And so we are neglecting to notice that mostly we have people living and generating heat at the outside of the space, which also happens to be where all the solar gains are. So on average, the suite is 25C, and it doesn't look like it's overheating in the model, but in actuality, the places that people are living are getting way too hot, and that's what the research is showing. So we end up with pull quotes of measured, this is not my building, but measured indoor bedroom temperatures of 30 to 31 during hot spells, overheating in bedrooms that were predicted by the PHPP tool to be acceptably cooled, exceeding 25C for more than 20% of the time. So this is a straightforward tool problem. Number 4. Do you remember how I said that we did all of that modeling and the modeling said it was going to be fine? And then we got the 2040 weather file and we used that and we said that was going to be fine. It turns out that the 2040 weather files that are mostly available are for a typical year. And the use case that's envisaged by the people who made that weather file is you predicting the future energy use of the building over an entire year. What they have not done is made a weather file that contains a 1 in 5 return heat wave or a 1 in 10 year return heat wave. So when you run it, you don't see the massive heat gains and temperature problems that might occur during unusual spells of hot weather. You're just getting what will happen on an average year. So, lesson learned. We can decide what we think a reasonable heat wave is and just run that 2-week period and see what our building does using our energy modeling tools, using our Energy Plus, modeling each of our suites with each of their rooms separately to try and get a better idea of what will really happen in those buildings. Culprit number 5, and this was me, at least in part when I started this project. So I had worked on a lot of small projects for people who were designing buildings that they were going to live in, like homes. I'd had clients who never turn on their air conditioning system that we built for them. I got a phone call and they said, my geothermal system's very chilly. And I said, that's great, well, tell me about how you're using it. And they said, well, you know, we turn on the heating in the winter and then we turn it off, and then the next year we turn on the heating in the winter. And I said, well, no, you have to balance the system. And they said, oh, well, but, you know, we feel guilty about running the air conditioning. There's actually someone in this room who phoned me and said, I feel guilty about turning on the air conditioning system, but I'm too hot, what do I do? Yes. So the thing is, I really was used to occupants that were really engaged. And it didn't occur to me that someone would say, you know, for allergen reasons or for ability reasons, our passive house windows are triple glazed. They're really heavy, and we've got these really big units of glass because we don't want people to have too much heat loss through the thermal bridges of smaller panes. And we want to give them the opportunity to have natural ventilation, but the result is that some people find it overwhelming to use the windows. And the passive house windows are also sometimes a different operating mechanism than they're used to. And so when you have tenants coming in and out of a rental suite, that can be a real challenge, right? People are very confused by thermostats, even pretty basic thermostats. And so it's really important that the system work and that if we let that system run away, same conversation as with the heat gain, that we can recover the suite temperature. If they call us and say, I'm having a problem, after you close the window for them, you help them with the thermostat, that the suite can recover quickly. So the next culprit is that we, at least I, am from a tradition, a venerable tradition, of building boxes with windows at eye height in it. I live in an old Victorian house and it overheats in the summer every year. I'm not from a tradition of building buildings that cool themselves in the summer. So some of the features that you see on the board here is a tower that can create a thermal stack effect, high windows or operable louvers that will draw heat out of a space and suck more cool air in at the bottom. I've got an example of a factory. This is for those who've been there, the University of Waterloo's School of Architecture in Cambridge. And it has this sawtooth roof that brings in light. All those windows, though, they face north. So we're getting light without solar gains. And some of those units are operable so that they get the stack effect out of the building. So these are buildings that are designed to let heat out in the summer. So if you don't have an air conditioning system for whatever reason, say you've had an electricity outage or you've had something break, you have some other way of dealing with the heat. But a lot of our passive house multi-unit residential looks more like this, right? Super insulated, wrapped in a blanket, minimal window area, not a lot of vertical access to multi-storied windows, not a lot of double-sided ventilation. We usually have double-loaded corridors because they're less expensive. We usually, for those of us who are really ambitious, we have solar, we have south-facing overhangs, and then we value engineer them out because they're too expensive. Thank you for the laugh. And then, the passive house connection, though, and this one's really important, is that we get credit in some of our certification systems for solar gains in the winter offsetting heating. So we have this incentive at the design phase to put solar heat into the building, to use higher solar heat gain glass, because it saves carbon on the heating side, but it creates a vulnerability and a health risk in the summertime. So this is where my hot take, I think my hot take comes in here. I believe that we in Canada at the moment have buildings that are more vulnerable in summer than in winter, and that as designers we may need to change our lens from this building is a health risk in the winter because when it fails people will be too cold and they could die, to this building is a health risk in the summer. If this building fails and people get too hot, they could die. I think that there are many more ways to heat a building. You can go and buy a $29.99 electric heater from Canadian Tire, but one window air conditioner costs $450 and it doesn't fit in most passive house windows. So you need to give people buildings that can allow them to self-cool properly. All right, culprit number 7. Failing to imagine what happens to temperatures when things go wrong. So this is another tie-in to passive building 101. For those who have done a lot of passive buildings in the room, what you know is that we super insulate the envelope. We have south-facing windows for solar gains, and then we put in a very efficient energy recovery ventilator. And if you dig back into why passive house, the original standard, used that 15 watt per meter squared, or I think it's 10 watt per meter squared, you guys can correct me. 10? 15. Is that it's what you can carry in the ventilation air. So that was the story I'd always heard, right? If you can carry it in the ventilation air, then you don't need 2 separate systems. You don't need to put in a whole separate fan. You don't need to buy all that stuff. You just take your energy recovery ventilator and you put a coil in it, and then you deliver the heating and the cooling with your ventilation air. That's the story. But the issue in our climate is that once you've lost the temperature in the building, then the capacity of the coil in your energy recovery ventilator, because you have an 85% efficient energy recovery ventilator, by the way, is 15% of what you need to cool the building back down. So now you're trying to deal with an overrun problem, and you don't have the tools to do it. So relying on that coil in the energy recovery ventilation becomes a really big vulnerability, not in everyday operation, but when things go wrong. Culprit number 8. This was another failure of imagination on my part. So like, I follow the standards, right? I sized my system for 31 degrees Celsius, 23 wet bulb. It's a great, great size. I didn't have any more capacity, and I also had a mission to not put any cooling in, so I thought I was doing well. But when I gave a talk at that building to a group of electrical engineers, it was 35 Celsius outside and 80% humidity. And that was 150% of my design load for cooling. In contrast, I had talked to somebody who'd put in an identical system to the one that I have in Kamloops in the mountains, and they had never had a problem. They said, we survived the heat zone event, and we never had a temperature overrun. So I ran the psychrometrics for them on 42 Celsius, 30% humidity is only 110% overrun. So the humidity in the East Coast climate makes us much more vulnerable to overheating, because first your AC system has to strip that humidity out before it can cool the air down. And we therefore need more robust HVAC systems to deal with potential future climate events. The numbers get big really fast, which wasn't something that I had really explored. Culprit number 9. It isn't working yet. So the last thing that we discovered was that we had built a building, we had handed it over to a client, and they actually didn't have anyone on staff or on the Rolodex who knew how to maintain a variable refrigerant flow system, which was the kind of HVAC system we'd given them. And we didn't think it was very complicated, but it turns out that at the design stage with a multi-unit residential building, it's really important to sit down with the eventual operators and make sure that they know who they're going to call. In a perfect world, have the person who installed the HVAC system give you a 3-year contract, or at least a 1-year with the option to extend, so that when you're trying to troubleshoot the system, the same people who put it in, who balanced it, who commissioned it, continue to support you over the lifespan. But in addition, if an owner says they absolutely don't have the capacity to train and maintain training for a unique system in their portfolio, it may be necessary to back up and decide to use a different system. So what we learned at 500 McNabb, and this was quite recent, was that because of a quirk of the programming of the variable refrigerant flow systems, they've only been outputting half their capacity for the last 2 years. So my building's overheating because it doesn't have enough cooling because they didn't turn on the cooling I gave them. We managed to get one of the 3 working this summer, and that side of the building has very rarely had many overheating events. When we go and look at people's thermostats, mostly they're fine. If they're not fine, then there's one suite out of the 18 who's exactly at outdoor air temperature, so we know that they've opened their windows. So this is incredibly important. I think people don't think enough about it. So in conclusion, thank you for listening to my tiny rants and hot takes. Multi-unit residential buildings, especially built to passive house standards, are vulnerable to overheating. There's a lot of evidence they're more vulnerable than the analyses suggest. They will be especially vulnerable if you use high solar heat gain glass. And I say high, I mean 0.35. I want to see 0.23s out there in the world. We've got a building with 0.18, and it works really well. They assume all occupants will be engaged and active in window, shade, and heat generating activities. They're modeled on suite or building levels and not a room level. They're designed with substantial unmet cooling hours because the tools are hiding the fact that 10% over 25 Celsius is happening. They're just giving you kind of a green signal and saying it meets the standard. The cooling capacity is limited. So a thing I often hear, I've still heard in the past 2 years with all this research out there is people giving interviews about passive house buildings and saying, the real challenge is that we can't get cooling systems that are small enough for our high performance buildings. And half a ton is the minimum, because we know that that 1 in 20th MERB resident just needs it just to deal with their cooking load and their light computer. So you can avoid it by using ASHRAE occupant loads for design, sizing coolings per room per suite, keeping summer solar heat gains out, providing generous in-suite peak capacities. So you can size your plant much smaller, just make sure that each individual terminal unit has a little bit more capacity. They're not all gonna run at once. So it's not an energy issue, but it is a comfort issue. Size your fresh air systems, looking at both the cooling and dehumidification and high latent design days. Include central plant redundancy, and then plan to figure out who's going to turn it all on. And if it comes to a conflict between certifying your building and doing all these other things I'm asking you to do, consider putting the cooling in instead of certifying the building. Extra hot take. Thank you, everybody.